The conveyor belt moves with the inevitability of a glacier, but what it carries is not ice. It is a river of color, a torrent of red and yellow and blue plastic bricks tumbling forward in mechanical procession. Each piece weighs mere grams, yet collectively they represent something far heavier. The accumulated refuse of a consumer culture that produces 200 million Lego elements every single day. This is the arrival bay of Lego's experimental recycling facility, a cathedral of industrial redemption where the past comes to be unmade. The air here carries the faint chemical signature of aged acrylonitrile butadiene styrene, a thermoplastic polymer engineered for durability, but now facing its own existential reckoning. The bricks clatter against stainless steel sorting trays, each collision a tiny percussion in a symphony of reclamation. Some pieces are pristine, their injection molded precision still evident after decades. Others are faded, their pigments oxidized by ultraviolet exposure, their surfaces abraded by the friction of play. But the machines do not discriminate. They process all with the same cold efficiency, because buried within every brick, no matter how worn, are the hydrocarbon chains that gave it shape, waiting to be liberated and reborn. The first station is deceptively simple, a cascade of tumbling drums where water and compressed air blast away the accumulated grime of storage. Dust from attics, basement mold, the microscopic residue of human touch, all of it must be stripped away before the real work begins. The drums rotate at precisely 47 revolutions per minute, a speed calibrated to maximize cleaning without fracturing the plastic. Inside, ceramic media the size of kidney beans scrub each brick surface, their abrasive geometry designed to reach into the hollow studs and recessed clutch mechanisms. The water is not ordinary tap water. It has been deionized and pH balanced to prevent chemical reactions that might compromise the plastic's molecular structure. As the drums thunder, steam rises in pale clouds, carrying with it the scent of detergent and dissolved organics. This is purification, but it is only the beginning. The cleaned bricks emerge onto a perforated conveyor where heated air, precisely controlled at 68 degrees Celsius, evaporates every remaining droplet. Moisture is the enemy of what comes next, because the optical sorting system cannot tolerate interference. Overhead, an array of hyperspectral cameras awakens. These are not the cameras of consumer electronics. They are industrial spectrometers capable of analyzing light across 170 discrete wavelengths, from deep ultraviolet to near infrared. As each brick passes beneath their gaze, xenon flash tubes fire in rapid succession, illuminating the plastic with controlled bursts of photonic energy. The reflected light is captured and decomposed into its spectral signature, a unique fingerprint determined by the plastic's chemical composition, additives, and pigmentation. The system is hunting for imposters. Not every brick that enters this facility is genuine Lego ABS. Counterfeit pieces made from polypropylene or polystyrene, damaged bricks with metal inserts, even occasional non-Lego toys, all must be identified and ejected. The analysis happens in milliseconds. Pneumatic jets fire with surgical precision, blasting rejects into a separate collection bin while approved bricks continue their journey. The rejection rate hovers at 8%, a testament to both the prevalence of contamination and the system's uncompromising standards. But color presents a deeper challenge. Lego bricks come in 53 distinct shades, each formulated with proprietary pigment blends and stabilizers. Red bricks contain cadmium-free iron oxide complexes. Yellow incorporates organic diarylide compounds. Blue relies on phthalocyanine derivatives synthesized through copper catalysis. To recycle these materials into new bricks of consistent color requires separation at a molecular level. The solution is another tier of optical sorting, yet this time focused purely on chromatic analysis. Advanced algorithms compare each brick's spectral data against reference libraries stored in industrial servers. The system does not merely identify red or blue. It distinguishes between bright red and dark red, between medium azure and dark azure, sorting into 27 discrete color families. Rejected colors are not discarded. They are diverted to holding silos where they await batch processing. Only after this ruthless triage do the selected bricks, now sorted by both material purity and color family, advance to the chamber where their molecular bonds will be systematically dissolved. The grinding hall is a realm of controlled violence. Industrial shredders the size of cargo containers stand in rows, their tungsten carbide teeth rotating at 1,800 revolutions per minute. Each tooth is precision machined to tolerances measured in microns, sharp enough to cleave plastic, but hard enough to resist the abrasive punishment of continuous operation. The bricks cascade into the shredder's waiting maws, and within seconds, they are transformed from recognizable toys into irregular shards, no larger than rice grains. The noise is apocalyptic, a shrieking, grinding roar that penetrates foam earplugs and rattles the steel catwalks overhead. But the violence serves a purpose. The smaller the particles, the greater their surface area, and the more efficiently they can be processed in the chemical stages to come. The shredded plastic exits through steel mesh screens, sized to ensure no particle exceeds 5 millimeters in any dimension. Oversized fragments are automatically cycled back through the shredders for additional reduction. The result is a coarse powder the color of confetti, a homogeneous mass that betrays no hint of its former identity as interlocking bricks. This powder enters the thermal decomposition reactor, a sealed chamber where temperature and pressure become instruments of molecular surgery. The reactor is a horizontal cylinder, 10 meters in length, lined with Inconel alloy to resist both heat and chemical corrosion. Inside, the temperature climbs to 420 degrees Celsius, hot enough to soften the ABS plastic, but not hot enough to trigger complete pyrolysis. The powder liquefies, becoming a viscous resin that flows like lava across heating elements embedded in the reactor floor. But heat alone does not purify. The reactor is flooded with an inert nitrogen atmosphere to prevent oxidation, and powerful agitators stir the molten plastic at variable speeds, ensuring uniform temperature distribution. Dissolved within the resin are contaminants, residual pigments from incompatible colors, degraded polymer chains weakened by years of UV exposure, trace metals from manufacturing additives. These impurities must be extracted, and the method is both elegant and brutal. Vacuum distillation. Pumps reduce the reactor's internal pressure to near vacuum, causing volatile compounds to vaporize and separate from the polymer matrix. The vapors are captured in condensation towers where they cool and liquefy, becoming industrial waste streams destined for specialized disposal. What remains in the reactor is purified ABS resin, stripped of contaminants, and ready for the most critical transformation of all. Repolymerization is where chemistry transcends engineering and becomes almost biological. The purified resin is transferred to a series of stirred tank reactors where it meets fresh monomers, acrylonitrile, butadiene, and styrene, in precise stoichiometric ratios. These are the building blocks of ABS, the three molecules whose union creates a plastic with exceptional impact resistance, thermal stability, and dimensional accuracy. The recycled polymer chains, though purified, have been shortened by thermal stress and time. To restore them to virgin quality requires grafting new monomer units onto the existing chains, a process called chain extension. Catalysts are added, typically organotin or peroxide initiators, to which activate the monomer molecules and allow them to bond with the degraded polymer. The reaction is exothermic, releasing heat that must be carefully controlled to prevent runaway polymerization. Cooling jackets circulate chilled propylene glycol through the reactor walls, maintaining temperature at exactly 130 degrees Celsius. The reaction proceeds for 6 hours, during which the liquid resin gradually thickens as molecular weight increases. Inline viscometers monitor the process in real time, measuring the resin's resistance to flow, a direct indicator of polymer chain length. When the target viscosity is reached, the reaction is quenched with termination agents, and the repolymerized ABS is ready for the final stages of refinement. But even repolymerized plastic is not ready to become a brick. The resin must be pelletized, transformed from a molten mass into uniform granules suitable for injection molding. The resin is extruded through a die plate perforated with hundreds of circular orifices, each 3 millimeters in diameter. Molten strands emerge like spaghetti, immediately quenched in a water bath to solidify them. A rotary cutter positioned at the die face spins at high speed, slicing the strands into cylindrical pellets as they emerge. The pellets tumble into the water bath, where they are cooled to room temperature and then conveyed to centrifugal dryers. These dryers spin at forces exceeding 15 gravities, flinging water from the pellet surfaces and leaving them dry to the touch. The finished pellets are indistinguishable from virgin ABS. Same density, same melt flow index, same mechanical properties. They are pneumatically transported through overhead pipes to storage silos where they await their transformation back into bricks. The injection molding floor is where polymer becomes geometry. Rows of hydraulic presses dominate the space, each machine a 20-ton monument to precision manufacturing. The molds themselves are works of art. Hardened steel dies machined to tolerances of 5 microns, their internal cavities shaped to produce bricks with the iconic Lego stud pattern. Each mold cavity is cooled by circulating water channels, drilled through the steel in serpentine patterns to ensure even heat extraction. The recycled ABS pellets are fed into the molding machine's hopper, where they descend into a heated barrel. Inside, a reciprocating screw simultaneously heats and compresses the plastic, raising its temperature to 240 degrees Celsius, the precise point where ABS flows like honey but has not yet begun to degrade. When the screw reaches its forward limit, the accumulated melt is injected into the mold cavity at pressures exceeding 1500 bar. The injection takes less than 2 seconds, but in that brief moment, molten plastic flows through the mold's intricate geometries, filling every corner, every undercut, every microscopic detail. The mold clamps shut with hydraulic force, holding the plastic under pressure as it cools and solidifies. After 28 seconds, timed to the millisecond, the mold opens and ejector pins push the newly formed bricks onto a collection belt. They are still warm to the touch, but their shape is already final. And each brick emerges with the clutch power, the precise interference fit between stud and tube that has made Lego legendary. The recycled bricks are identical in every measurable way to those made from virgin plastic, a fact verified by the battery of tests waiting downstream. Quality control is not a checkpoint, it is an obsession. Every batch of recycled bricks undergoes destructive and non-destructive testing. In laboratories that resemble pharmaceutical clean rooms, tensile strength testers pull bricks apart to measure their resistance to deformation. Impact testers drop steel weights onto bricks from controlled heights, recording the force required to fracture them. Dimensional metrology systems, coordinate measuring machines with laser scanning heads, verify that each brick's geometry matches specifications to within 20 microns. But the most critical test is clutch power, the force required to separate 2 connected bricks. A robotic test rig connects bricks in standardized configurations and then pulls them apart while load cells measure the separation force. The target range is narrow, 25 to 35 newtons for a standard 2x4 brick connection. Too weak and structures collapse. Too strong and children cannot separate them. The recycled bricks consistently fall within specification, their molecular structure so thoroughly restored that even advanced polymer analysis cannot distinguish them from virgin material. But the laboratory tests reveal something unexpected, a phenomenon that transforms recycled plastic from a compromise into an advantage. The repolymerization process, by breaking and reforming polymer chains, OS has eliminated internal stresses locked into the original bricks during their first molding. Virgin ABS, when injection molded, experiences thermal gradients that freeze molecular tension into the finished part. Over time, these stresses can cause warping or brittleness. The recycled bricks, having been melted and repolymerized, exhibit lower residual stress and greater long-term dimensional stability. They are, in a measurable sense, superior to the originals. This discovery shifts the entire paradigm of plastic recycling, from salvaging waste to creating enhanced materials. The engineers document their findings in technical papers submitted to polymer science journals, providing quantitative evidence that closed-loop recycling can yield performance improvements, not just environmental benefits. The facility operates on a scale that defies intuition. Each day, 11 tons of used Lego bricks enter the system. After sorting, cleaning, grinding, repolymerization, and molding, 9.2 tons of new bricks emerge, a material recovery rate of 84%. The remaining 16% is not waste, but byproduct. Pigments extracted during purification become raw materials for industrial dyes, while degraded polymer fractions are sold to manufacturers of lower-grade plastics. Nothing is incinerated, nothing is landfilled. The facility has achieved what most recycling operations only aspire to: true circularity, where products flow in an endless loop from consumer to factory and back again. But achieving this required more than technology. It required rethinking the entire supply chain. Lego established collection points in 43 countries where families can drop off unwanted bricks. The bricks are consolidated at regional hubs, sorted by volunteers, and shipped to the central recycling facility in Denmark. The logistics are staggering. Container ships, freight trains, and diesel trucks burning fossil fuels to move plastic across continents. Critics point to the carbon footprint, arguing that the transportation emissions undermine the environmental benefits. But life cycle analyses tell a different story. Manufacturing virgin ABS from petroleum requires 4.6 kilograms of CO2 equivalent per kilogram of plastic. The recycling process, despite its transportation burden, emits only 1.8 kilograms per kilogram, a 61% reduction. When scaled across Lego's annual production of 75 billion elements, the carbon savings are measured in hundreds of thousands of tons. Yet the true significance extends beyond carbon accounting. Lego's recycling system exists as proof of concept, a demonstration that complex, high-value plastics can be recovered and reused without sacrificing quality. For decades, the plastics industry has argued that technical limitations make true recycling impossible for engineered polymers. Lego has shattered that assumption. The facility's existence challenges every manufacturer that continues to design products for obsolescence, that chooses virgin plastic over recycled content, that treats waste as an inevitable externality. The message is stark. If a children's toy can be recycled to original specifications, then so can automotive components, medical devices, and consumer electronics. The technology is not exotic. Hyperspectral sorting, thermal depolymerization, and reactive extrusion are all established industrial processes. What was missing was not capability, but commitment, not innovation, but incentive. Lego invested 200 million euros to build this facility, a sum that will not be recovered through material savings alone. The company views it as infrastructure for a post-disposable economy, a bet that regulations and consumer preferences will eventually make circularity mandatory rather than optional. The bricks that emerge from this system carry no visible mark of their recycled origin, no label proclaiming their environmental virtue. They are sorted, packaged, and shipped to retail stores where they sit on shelves beside bricks made from virgin plastic, indistinguishable to consumers. This anonymity is deliberate. Lego does not want recycled bricks to occupy a separate, lesser category, a good enough alternative for environmentally conscious buyers. The goal is equivalence so complete that the distinction becomes meaningless, where every brick could be recycled without anyone noticing or caring. This is not greenwashing. It is integration. The recycled content is not highlighted in marketing campaigns or printed on boxes. It is simply absorbed into the global supply of 40 trillion Lego elements currently in circulation. In this way, the recycling facility does not create a new product, but quietly transforms the existing one, changing the chemical composition of childhood one brick at a time. Outside the facility, the sky is the pale gray of Baltic winter, and the wind carries the salt tang of the North Sea. Inside, the machines run in 3 shifts, their operations continuing through night and holiday, relentless as tides. The engineers who designed this system know that it is not a solution, but a prototype, a first iteration that will evolve as technology advances and scale increases. Already, plans are underway for second-generation reactors with higher throughput and lower energy consumption. Researchers are investigating advanced catalysts that could repolymerize plastic at lower temperatures, reducing thermal stress and further improving material quality. There is talk of expanding beyond ABS to tackle the harder problem of mixed plastic waste at the low value, contaminated streams that currently have no viable recycling pathway. But for now, the focus remains on perfecting the system that exists, on refining each stage until efficiency reaches theoretical maximums. The final act in this industrial drama occurs in a space that most visitors never see, the Quality Archive, a climate-controlled vault where samples from every production batch are stored indefinitely. Each sample is labeled with molecular traceability data, the date of collection, the region of origin, the color family, the batch number from repolymerization. This archive exists as both quality assurance and historical record, a library of plastic that chronicles the evolution of recycling technology. Decades from now, when LEGO's current facilities are obsolete and new methods have rendered today's processes archaic, researchers will return to this vault to extract samples and study them with instruments not yet invented. They will measure degradation rates, analyze polymer architecture, and compare historical data against future performance. The archive is a gift to the future, an admission that the work of sustainability is never finished, that each generation must improve upon the last. In the end, what LEGO has created is not just a recycling facility, but a philosophical statement rendered in steel and polymer. It declares that permanence and disposability are choices, not inevitabilities, that the materials we extract from the earth need not become the garbage we bury in the earth, that engineering can serve conservation as readily as consumption. The machines here do not simply process waste, they challenge the concept of waste itself, asserting that in a properly designed system, there is no such thing as garbage, only resources temporarily out of place. Every brick that passes through this facility carries that message forward, a small plastic ambassador for an industrial future that might yet reconcile growth with stewardship. The children who play with these bricks do not know their history, do not sense the molecular resurrection that preceded their arrival. But perhaps that is the point. The most profound transformations are the ones that become invisible. The systems that work so seamlessly, they disappear into the fabric of the ordinary. This is the promise of true sustainability, not sacrifice, not compromise, but abundance, reimagined with the same carbon atom cycle endlessly through forms and functions, never depleted, never discarded, forever renewed.